this section, we're going to learn about acid-base titrations. It's again a very useful concept and useful hands-on tool that we're going to learn in the lab. Okay, acid-base titrations. So what is a titration? In a titration, the concentration of one solution is used to determine the concentration of another one. In an acid-base titration, a standard solution of base is usually added to a sample of acid of unknown molarity. So, do you understand? So, we know the concentration of base, but we don't know the concentration of acid. Or sometimes you can do the other way around too. You can do a titration with the known molarity of acid and unknown molarity of a base. Both ways are possible. Okay. In an acid-base titration, we also need to use an indicator. So, indicator tells us if a titration has reached its end point. Okay, so I'll explain to you what are these endpoint and all that. So in order to find out if it has done the titration, we need to add an acid-base indicator. So in an acid-base indicator, it has different colors in acid and it has a different color in a base. And we use that to monitor the reaction progress. At the equivalence point, meaning when the number of moles of hydrogen ions are equal the number of moles of hydroxide ions. That's what happened at the equivalence point. The mole of H plus from the acid equals the mole of hydroxide ion produced by the base. Amount of H plus ion in the flask equals the amount of hydroxide ions added. The end point occurs when there is a slight excess of base and the indicator changes color permanently. You may have not understood any of these that we talked about in this slide, but I'll show you this with a diagram and that will make more sense. Okay? Okay. So this is how an acid-base titration is done. Normally, you're going to do it with a Erlenmeyer flask. And then you put your acid into the Erlenmeyer flask. Any amount would be fine. Sometimes we use 10 milliliters, 25 milliliters. So you put a certain volume of your acid into the Erlenmeyer flask. And then you're gonna use a burette. Burette is a long tube. It has a stopcock at the end, like a tap, so you can open and close it. And then in the long tube is graduated, meaning it has marks to tell you what is the volume of the base that is being added from the burette. So your acid H plus in the Erlenmeyer flask and the base is in the burette, let's say sodium hydroxide. So you have H plus, OH minus coming. So H plus X minus is the counter ion. For example, let's say we are doing this experiment with HCl and sodium hydroxide. So we are going to form sodium chloride and water. Okay, so hydrochloric acid you can consider in the flask and sodium hydroxide you can consider that's in the burette. Now initially you have a certain amount of H plus ions, number of moles. You keep adding hydroxide from the burette and it's going to keep on forming water molecules. And you have to add an indicator inside the flask. Okay, and the indicator most commonly used for the acid base, strong acid, strong base titrations is called a phenolphthalein. Phenolphthalein indicator is clear in the acidic medium, but when it becomes basic, it would become pink in the basic medium, meaning if you have more base, it would become pink in color. As long as we have the hydrogen ions in the flask, You see, you keep on adding hydroxide from the burette, and then as you add it, you can see some slight amount of pink color, more concentrated, where it touches the hydrochloric acid. But when you shake or you swirl the Erlenmeyer flask, this is going to disappear, because the hydrogen ion and hydroxide ions are reacting to form water molecules. And then you keep on adding hydroxide from the burette, and at a certain point all the hydrogen ions inside the flask will be done reacting with hydroxide. You add more, but there are no more H plus ions to react with hydroxide ions. And at that point, when the number of moles of H plus equals the number of moles of hydroxide ions added, we call that as the equivalence point, meaning the same number of moles are being reacted now. Okay, the indicator will not change during that time, but then you just add one drop or maybe a slight excess of hydroxide ions. There are no more hydrogen ions to react in the medium, so this whole flask will become now sodium hydroxide. Even with one drop will make the whole flask basic, so the indicator changes color to pink, and you swirl the flask and it's not going to change anymore, so it's going to keep remaining as the pink color for the solution, and we call that as the end point of the titration. At that point you stop adding any more sodium hydroxide or the base from the burette. Okay, so first we need to know, when we first started, what is the volume of the sodium hydroxide that we started with, and then at the end also you're going to write down what's the amount of sodium hydroxide you have added by looking at the level of the base in the burette. From the two, we know how much sodium hydroxide has been added. That's the volume of sodium hydroxide added. Okay, and if you know the molarity of sodium hydroxide and you know the volume, then the number of moles are going to be 1 to 1. We can find out the molarity of acid. Okay, and let's see how we're going to use a titration to find out the concentration of an unknown acid or a base by looking at an example, okay, in the next slide. But basically this is how a titration is being done. Okay, a standard solution of 0.243 molar sodium hydroxide was used to determine the concentration of a hydrochloric acid solution. If 46.33 milliliters of sodium hydroxide is needed to neutralize 10 milliliters of the acid, what is the molar concentration of the acid? Okay, we have the other page also. Okay. Now again we're going to be using with a burette. So this is a burette, a long glass column. It has a stopcock at the end. So this is graduated to tell us the amount inside. Normally the starting point, when it is completely filled, it is 0, 0, meaning nothing has been added. At the very end you have 50 milliliters. Excuse me. You can fill the burette up to 50 milliliters. You start with 0 or maybe a number below that is fine too, and then it goes from 0, 1, 2, 3 like that up to 50. Okay, and then you're going to have your flask there, and a standard solution of 0.243 molar sodium hydroxide. 0.243 molar sodium hydroxide is in the burette. Determine the concentration of hydrochloric acid, so HCl here. If 46.33 milliliters of sodium hydroxide needed, so from the burette it has been added 46.33 milliliters to neutralize 10 milliliters of the acid. So we have 10 milliliters of the acid here. We want to find out the concentration of hydrochloric acid. Okay. Now, sodium hydroxide. The known amount, we know the molarity. We also know the number of moles by looking at the volume. We know the volume and the molarity. Now, from the volume and the molarity, what can we find out? We can find the number of moles. And then by looking at the balanced equation, we can see what is the molar ratio. And then we can find out the concentration of hydrochloric acid. So first we need to write the balanced equation. So we have sodium hydroxide plus HCl giving you sodium chloride and water. One sodium, one chloride, one chloride, two hydrogens, one oxygen. It is balanced. Okay. Sodium, we can find out the number of moles of sodium hydroxide. Remember, molarity equals moles over volume in liters. So the number of moles sodium hydroxide would be then molarity times volume, M times V. Okay, M is 0.243 moles per liters multiplied by the volume. 46.33, you need to convert it to liters. They would be 0.04633 liters, and that will give us the number of moles as 0.243 times 0.04633, 0.0113. That's the number of moles of sodium hydroxide. Now, if you look at the balanced equation, the molar ratio is 1 to 1, right? So, if it is 1 to 1, then we can find out the number of moles of hydrochloric acid. Okay. So let's go to the other page and find out 0.0113. So moles (0.0113) sodium hydroxide, and then the molar ratio is 1 mole sodium hydroxide react with 1 mole HCl. So then we find the number of moles HCl, hydrochloric acid, also 0.0113 moles. And the volume of hydrochloric acid is 10 milliliters. Now we know the volume, we know the number of moles, we can find out the molarity. That's going to be moles over volume in liters, 0.0113 moles. You divide it by converting milliliters to liters, 0.010 liters. Okay. So this will give us 0.0113, 0.01, that's easy calculation, 1.13. 1.13 moles per liters. In other words, 1.13 is the molarity of hydrochloric acid. Okay, that's how you use acid-base titration to find out the concentration of an unknown acid solution. That's the molarity of hydrochloric acid. Let's look at another example. A 50 milliliter sample of sulfuric acid is titrated with 0.1524 molar sodium hydroxide. The burette reads 0.55 milliliters at the start and 33.87 at the end. Find the molarity of the sulfuric acid solution. Again, so we have a burette and then you have your sulfuric acid in the flask. Sulfuric acid, H2SO4, 50 milliliters, titrated with 0.1524 molar solution of sodium hydroxide, which is going to be in the burette. The burette reads 0.55, meaning it started at 0.55 milliliters. And then the end point, once hydroxide is being added, it ended at 33.87 milliliters. Now from these two readings, we can find out the volume of sodium hydroxide used for the titration. Okay, and then we know the volume, we also know the molarity. You can find the number of moles. Look at the molar ratio from the balanced equation, and similar to the previous question, we can find out the concentration of sulfuric acid. First, we need to write the balanced equation. So this is the balanced reaction. Sodium hydroxide with sulfuric acid going to form sodium sulfate, Na2SO4, and water. Okay, so since there are two, you need to put 2 right there, and then 2 water molecule. So the volume of the sodium hydroxide from the 2 data given for readings, when you subtract this amount from here, you can find out the volume of the base. And then to find out the number of moles, remember molarity equals moles over volume. So number of moles would be M times V. V is the volume, which is in milliliters, convert into liters, multiplied by the molarity of sodium hydroxide, will give you this many number of moles of sodium hydroxide. Now the molar ratio is 2 moles of sodium hydroxide react with 1 mole of sulfuric acid. Since 1 mole of sulfuric acid react with 2 moles sodium hydroxide, the amount of sulfuric acid. So you're going to use the molar ratio. This is the number of moles of sodium hydroxide. Molar ratio, 2 moles sodium hydroxide react with 1 mole sulfuric acid. So basically you divide this number by 2 because it's 2 to 1. Okay, that's the number of moles of sulfuric acid. We use 50 milliliters of a sample. So molarity is moles over volume. Moles, you just found out. Volume converting into liters, find the molarity of sulfuric acid. Okay, so that is how we use acid-base titration to find out a concentration of an unknown acid, and we can use the same way to find out the concentration of an unknown base. Okay, let's start the oxidation reactions in the next session.